All right, in this video, I want to go over some of the background for the impulse excitation method that we're using to determine the elastic properties of our 4140 steel. And then I also want to go through briefly the calculations needed to obtain those properties. So let's start with kind of the basics of this. So it's a non-destructive technique in which we have a material like our 4140 steel that's supported, and we hit it with some type of little hammer or mallet. And this minimal force causes it to vibrate at a resonant frequency. However, it doesn't cause any damage to the sample. And it vibrates at that resonant frequency, causing a sound wave to exist or to be emitted. And we use that to determine the vibration of the bonds, which therefore harkens back to the elastic modulus and other elastic properties of the material. So in terms of the sound that's emitted, the sound is controlled by the material itself, the elastic properties, but also the geometry. And so we find that if we have a thin bar and a thick bar, the thin bar exhibits a low pitch material, higher frequency, the lower frequency, and then a thick bar has a higher frequency. So this is just geometric effects. Same material, different geometry. Also, if we compare long and short, the long will create a low pitch and the short will high pitch or high frequency. And so these are all things that you can hear with your ears, along with the software that we have to calculate these values. All right, so we use a standard for measuring these frequencies, and that's ASTM C1259. It's available in Canvas for you, and also there's a handout I developed based on that, and all of those are in Canvas for you to find, and this is just kind of a recap of that. So we have two different modes to calculate elastic and shear modulus, as well as Poisson's ratio. We have Flexure, which is illustrated here, where we have supports at certain lengths, and then it vibrates kind of up and down as you saw before. This is known as out of plane frequency or Flexure. And then we also have torsion, which is kind of a twisting of the bar, and this measures the shear modulus. So we get the elastic modulus from the Flexure mode and shear modulus from the torsional mode. And so the first thing we need to do is we need the sample dimensions and mass for the material that we have. So you probably saw this in the video on actually using our equipment. So we take the dimensions and mass, we build the supports, and the supports are at 0.224 times the length. So we need to know the length first. And so then we put some foam supports in those node positions that we see. And then we also have across supports that you see here for torsional mode as well. So after the supports are made, after dimensions and mass are taken, then we place the microphone in the hammer or striking tool, which is just a ball bearing attached to a flexible piece of plastic. So in this case, you strike the material right in the middle in Flexure with the supports here and here, and then the microphone goes on the end, right in the center on the end in the microphone position. So M for microphone, X for striking. And then the in torsion or torsional mode, we have it on the crossed supports, and we strike right on the Flexure mode nodal line that was there before, and we place the microphone on basically the adjacent one opposite over here in this position. So we have a microphone here and then strike it here. So once we've done that, the software will give us the resonant frequency for those two modes. And so then we can calculate elastic and shear modulus. But let's first take a look at one more thing. So in the calculation of modulus, there is a correction in this called T1. So T1 here, as you can see here, is a correction factor. And we use basically this version. However, if the length is 20 times the thickness or greater, then we can simplify that correction to just this equation. So I have you in our lab do this so that it saves you the calculation. So you can only do that. You only have to do this as opposed to this calculation here. So that's one more thing to look at when you're looking at the length and the thickness of the sample. But afterwards, we can calculate the modulus. So we have the correction factor here. And then if we kind of go through the others, lowercase t is the thickness. Capital L is the length of the bar in millimeters, as you can see over here. We have B, which is the width in millimeters. And then we have mass in grams. And we have this F of F, which is the fundamental resonant frequency in Flexure. So this is the frequency that you get from our software when it's in the Flexure mode. And then we also have a constant out in front. So plugging all that in, we'll get the Young's modulus or elastic modulus in pascals. And so then that can be converted to gigapascals or megapascals. So that is how we get the elastic modulus. So basically we need dimensions, mass, and then this frequency that we get from the software, and we can put all that in and obtain a value. All right, so now for shear modulus, which is not directly asked for in this lab, but it's a useful calculation to make. But the shear modulus is done from torsional. And so if we show the shear modulus G, we can calculate that based on length, mass, the frequency in torsion, width, and thickness, as well as another term R, which you can see here is relatively long, but basically incorporates the width and thickness and length and so forth. So those are just a couple more things that we can consider to do this. So in this, again, it's going to be in pascals. All the other length measurements are the same, and it'll give us in pascals. And again, we can convert to gigapascals or whatever. And from those two measurements, that allows us to calculate Poisson's ratio by knowing the Young's modulus or elastic and the shear modulus. And this equation is only valid when we have what's called an isotropic material. So that is something that has no preference towards direction. And so that's a useful assumption for us to make, that there isn't any anisotropic behavior in this material. So those are some of the calculations we can get from the impulse excitation technique. And again, this all relates to the handout on impulse excitation on how to perform the test, as well as the video on actually how to operate our equipment. And then again, this is from the equations and so forth are taken from ASTM C1259, which you can also find in Canvas, which has more information on how this test is performed and so forth.